Hey guys, so in this video we're going to do an extension of Markov chains. So it's not, the content here isn't directly accessible, but rather it's more to improve your understanding, familiarize yourself with the concepts, and also if you're finding this stuff interesting and that you feel like you have a grips on it, this may cement your understanding as well as show a bit more insight to some of the concepts. So the first part is that, the first thing I'll talk about is looking at how the equations we've set up relate to the transition matrices. And then the second is looking at the long run and looking at mathematically why the steady state doesn't affect it with regards to the transition matrices. So firstly, we'll go to this example just so we can get a transition matrix. We've done these in a lot of previous lectures. So 100 students either curry or pizza at school. So we get the transition matrix here where we're talking about P and C. So looking at PP, we have 40% if they'll eat pizza again, if they eat pizza, so pizza. So 0.4, which means that has to be 0.6. And then 70% chance they'll eat pizza if previous was curry, so this is previous, this is current. So this becomes 0.7, and then we'll have 0.3 here. Okay, so we now have this matrix. Now, if we set up these equations like we've done previously, we'll say that we have pizza here, and that pizza, so the number of students, the probability of pizza is equal to 0.4p plus 0.7c. And we can get that from the equations. We set this up before. And then if we can say for curry, well, curry is equal to 0.6p plus 0.3c. And we can see straight away these are very interlinked. The transition matrix is literally this 0.4 and 0.7, which is the direct line from up here, and 0.6, 0.3 is here. You can see the transition matrix with the PC. PC is effectively a matrix form of these two equations. So the P2 equals 0.4p plus 0.7c, and the curry is equal to 0.6p plus 0.3c. So that's an interesting thing to note, and it's a good way to check if you're not sure if your transition matrix is right. Then you can always just write out these equations and see if it relates to your matrix. So the second thing is looking at the long run steady state, and why with regards to this equation, so the Sn is equal to T infinity times S0, why that mathematically doesn't affect it. In regards to it doesn't matter what the numbers are as long as they add up to 1. Now with T is equal to, let's say, like three numbers, so it doesn't matter what they are, but it's a 2 by 2 matrix. Now when you have T to infinity, what happens is T converges to have two numbers here, A and B. And I'm just letting A and B, they're a real number. So for example, A could equal 0.4 and B could equal 0.6. And then we have SO. So SO is equal to two numbers, C, D. And for probability, the only condition about these is C plus D is equal to 1. So I'm letting C plus D be any real number. So it doesn't matter what basically it's every single initial condition possible. Now we're going to sub this in and see what we get, what the result is. So we'll say that Sn is equal to T infinity times S0. So all we get is we get AA BB, and we times that by S0, which is CD. Now we do some matrix multiplication and we get AC plus AD, BC plus BD. Then we can take out a common factor of A, and we get C plus D, and then B, C plus D. Now, referring back to here, we have our equation that c plus d is equal to 1, because remember these are just like the probabilities. Now we have c plus d, so we can just sub this into here. So like using 1. Okay, I'm going to rub this side off. And then we have it equal to A1, B1. So we get A, B. So in the long run, so this is S infinity. And you can see that no matter what the initial condition was, you still get this final result. And the initial condition does affect, like if you got rid of the initial condition, you wouldn't get the same result. But no matter what numbers you put in there, as long as they add up to 1, you'll get this long run steady state, which is equal to A, B. Now just quickly, if you're using the number of people, you could have C plus D equals whatever number it is. So let's say, example, that C plus D is equal to 200. Now it's the exact same thing, but when you get to this stage here, so we have this stage A, C plus D, brackets B, C plus D. Now we can sub in C plus D is equal to 200. So what we get is we get 200A, 200B. And relating this back to the formula, this shows us once again that NP holds. That it was a probability times n, where n is a total number, n, and p, you can see here, where the probability p is equal to A, B, which is derived from here. And you can see that this does hold, where NP is that, and the transition matrix is sub it in, and we can see that this result is the same.